Hello everyone, welcome to today's class and today we will going to discuss about specific heat capacity of gas. If you still didn't watch the previous video on thermodynamics, then just go and watch that uh, because this lecture is one kind of continuation of that part. So you must watch that video to start with this video. So let's start. Now, if you think about heating a gas, so you can heat up a gas in different way. That means you can fix the volume of the gas and then you can heat it up it, or you can fix the pressure of the gas and then heat it up. This in both these two cases you need to different amount of heat to heat it up the same amount of gas at the to the same temperature. Okay, so that means from here we just come into the conclusion that this gas must have two different specific heat capacity depending upon how we are heating up this gas. Okay, so first thing is specific heat capacity at constant volume. That means we are heating up the gas at keeping its volume constant. And second one is specific heat capacity at constant pressure, where we are heating up the gas keeping the pressure of the gas constant. Okay, so in both the cases uh, we are going to heat it up the gas by the same amount. And as we know, to define specific heat capacity we have to take unit amount of gas. That means 1 gram of gas or 1 kg of gas, and we have to heat it up that gas uh, by unit temperature. That means we have to increase the temperature of gas by 1 degree centigrade or 1 Kelvin. And for the first case, when we heated up the gas at constant volume, the amount of heat required is called specific heat capacity at constant volume, and for the constant pressure it is called specific heat capacity at constant pressure. That means specific heat capacity at constant volume is defined as the amount of heat required to increase the temperature of 1 kg of gas by unit that means by 1 degree centigrade. The amount of heat required is called the specific heat capacity at constant volume. Or if you want to change the temperature of the unit mass of the gas by 1 degree centigrade at constant pressure, then that will be called the specific heat capacity at constant pressure. Now uh, there is another specific heat capacity called molar specific heat capacity, and here we already also have two different molar specific heat capacities. One is at constant volume and another one is defined for constant pressure. So molar specific heat capacity at constant volume is defined uh, in similar manner, like instead of using 1 kg of gas we have to use 1 mole of gas. So for that case, molar specific heat capacity is defined like that: 1 mole of gas is at heated to 1 degree centigrade at keeping the volume of the gas constant, and the amount of heat is required is called the molar specific heat capacity at constant volume. And same thing at constant pressure is called molar specific heat capacity for constant pressure. But the molar weight of the gas, if it is capital M, now this small CV, that is the specific heat capacity at constant volume, and this is capital CV, molar specific heat capacity at constant volume, they are linked by this equation. Capital CV is M times the small CV. Reason behind that, this small CV is defined for 1 kg and this capital CV is defined for 1 mole, and as we know, the 1 mole, that is the molar weight, is capital M. That means 1 mole of gas means m kg of gas, and 1 kg, for 1 kg unit, the CV, small CV amount of heat, that means that much of heat. That means capital M amount of for capital M amount of gas you need M multiplied this small cv amount of heat. Okay, so this whole amount of heat is required to change the temperature of 1 mole gas by 1 degree centigrade, and that is called the molar specific heat capacity, capital cv. Okay, and by the same way we can get this equation, capital cp is exactly capital M into small cp. Okay, so this is, so far we just learned about the specific heat capacities, those are defined for the gas. And now next question is, which one is greater? That means, is it cp, that is the molar specific heat capacity at constant pressure, is greater than molar specific at heat capacity at constant volume, that it means cv, or vice versa, that means cv is greater than cp, which one is greater? Now we will going to see that. Let's start. So we are going to find the relationship between capital cp and capital cv. Now let we have n mole of gas, and we want to increase the temperature of the gas by amount of dt. Okay, so now to increase the temperature of gas keeping the pressure constant, it will be dqp equals to n into cp into dt. This equation looks exactly like the equation we already know, that is q equals to mct. Q equals to mct, that is a mass into specific heat capacity into change in temperature. So for our case, it is not mass, we want to increase n mole of gas, temperature of n mole of gas, so that is n. C is your specific heat capacity. Now we are going to increase the temperature at constant pressure. So at constant pressure, that's why we use capital cp, and we want to increase the temperature by dt, so that means it is dt. So this equation is actually this one. Okay, so now same thing, if we want to go for a constant volume, that means we want to keep the volume constant, and we want to change the temperature dt again of the same gas, same amount of gas, but now we want to keep the volume constant, then heat is amount of heat is required, dqv equals to ncv dt. Again this is m, that means this one is actually mass, this one is specific heat capacity, and this one is your change in temperature, like this formula. So this one is mass, as we don't have mass, we have the mole, so that is a for n mole, and this is cv, that is the specific heat capacity, and this is dt. Okay, so this equation can also be found by using the basic definition of cv or cp, as cv or cp is defined for a unit mass, or sorry, for a unit mole and unit temperature. So if you want to increase the temperature of the gas of mass, or of n mole of gas, or to a temperature of 10 degree or 15 degree, you have to multiply the number of moles you get, and also the temperature of the gas you want to increase with the cv. Okay, so now dqv is ncv dt. Now from the first law we can write dqv is your du plus dw equals to ncv dt. Now for to, if you actually going to keep the volume constant, so work done dw equals to pdv, you will get it 0, because your volume is constant, that means the change in volume dv is 0, that's why pdv, that is the work done, is 0. Okay, so by putting dw is 0 here, you will get du equals to ncv dt. Okay, so ncv equals to du dt, that means this is the ncv, that is the specific heat capacity at constant volume, is just 1 by n times of du dt. Okay, so du dt is can be called as the variation of internal energy with respect to temperature, with respect to the variation of the temperature of the gas. Okay, so that's how we actually define the cv. Okay, now using the same equation for dqp, dqp is your ncp dt, and dqp can be written as du plus pdv. Why this is du, because in the both cases, during the constant volume case or during the constant pressure case, you actually increase the temperature of the gas by the same amount. In both the cases you have increased the temperature by dt, so that means the internal energy for both the cases will be increased by the same amount, because the temperature of the gas is a complete function of the internal energy, or rather we can say internal energy of an ideal gas is the only function of temperature. That's why when you are actually increase the temperature for both the cases by the same amount, you have actually increased the internal energy in both cases by the same amount. Okay, so that's why it is also du. Okay, since you have increased here also the temperature dt, so that will be your du plus pdv. Since here volume is not constant, we will get some amount of work from here. So ncp that means ncv we can write du as ncv from our previous discussion. Okay, so you can write du equals to ncv from here. Now your du is your ncv. Now take this term to the right, you will get ncp minus cv equals to pdv. This is going to our equation 4. Now for n mole of ideal gas we can write pv equals to nRT. Okay, now we have to differentiate the equation to get the value of pdv. Okay, so now pdv, that means keeping p constant, if we differentiate the equation we will get this p is constant, that means v will be differentiated. So pdv equals to nr, both are the constant to the right side of the equation, so dt will be differentiated, we will get pdv equals to nr dt. Okay, so p is constant, that's why it is not differentiated, it's only v is differentiated here, so pdv equals to nr dt. Now just put the equation here. Okay, so you will get ncp minus cv dt, that this one equals to pdv, instead of pdv you will get nr dt. Okay, n will cancel and dt will cancel, you will get cp minus cv equals to r. And as you know, this cp, this is heat required to increase 1 mole of gas to temperature 1 degree centigrade. So that means that has a unit of calorie per mole Kelvin or calorie per mole degree centigrade, or but the R, that has the equation of joule per mole Kelvin. So that means the equation don't have the equal units on the left and the right side of the equation. That means we have to change the equation for our use. That is not actually exact according to their units. So that means uh, so the actual equation that we usually use it, that is cp minus cv equals to r by j, that is j is the joule constant, and as you know it has a dimension of joule per calorie, r has a dimension of joule per mole Kelvin. So that means joule will cancel, and that r by j term will get the unit of calorie per mole Kelvin. Okay, so that equation is good, and it is actually fine, and it's actually holding the unit on the both side of the equation. Okay, so next thing that we will learn in today's class, that will be the process. Okay, so what is a thermodynamic process? So thermodynamic process, as we all know about the already know about the state, thermodynamic state, equation of state, equilibrium. So the process is actually called how a system actually change its thermodynamic state. That means a system is let in an equilibrium state, that is shown in the PV diagram by P1, V1 and T1. This is the present state of the system. Now after some time, let this system takes the final equilibrium state at P2, V2, T2. Both the states are equilibrium states. Okay, so that means uh, how this changes happen to the system is known as a process. That means process is a way how system actually travels from one equilibrium state to another equilibrium state. Okay, so this is called process. So there may be different type of processes. Now for our case, mainly we will learn about isothermal process, adiabatic process, isobaric process, isochoric process. There is another process that is called cyclic process, where the final equilibrium state is and the initial equilibrium state both are the same. Uh, that means the system actually starts from here after traveling lots of distance over this PV graph. It actually again returns back to the initial equilibrium state, and this type of process is called our cyclic process. Okay, now let's start with the different type of process. As I already mentioned, the isobaric process where P pressure is constant, isochoric process where the volume is constant, isothermal process as the name suggests temperature constant, and adiabatic process that is called where the heat exchange is prohibited. That means there is no heat exchange happens during the adiabatic process. Okay, so let's start with the isothermal process. This is the first process of our discussion, today's discussion. So as we know, the isothermal process actually from the name is it suggests that the temperature of the system must remain constant during the change. So during a process actually system actually change its pressure, volume, temperature. That means it can change actually it can change its pressure, volume or temperature, but for isothermal process system doesn't change its temperature, it only changes its pressure and volume. So change temperature remains constant. And as we know from our previous discussion, du, that is change in internal energy, is actually n into cv into dt. So if temperature doesn't change, that means dt is 0, that means du equals to 0. That means internal energy of the system remain constant or remain fixed during a isothermal process, during an isothermal process. So that means the change in internal energy is not uh, allowed during the isothermal process. Okay, so if you use the first law, that you will get du equals to dq equals to du plus du dw. Du is your 0, that means dq equals to dw. That means the amount of energy, that means the amount of heat you actually supplying to the system, it's completely converted into the work done. That means there is no loss of heat. uh, there is no loss of heat. The complete heat is actually the whole amount of heat supplied to the system is completely converted into the work done. Okay, so but this process is a slow process. Reason is that this process doesn't show you this process doesn't show you the heat exchange is 0. That means system have to exchange heat with the surroundings, and if the system do some amount of work or some amount of work is done on the system, in both the cases system have to exchange heat with the surroundings. When the system actually do some amount of work, that means it actually expenses some amount of energy to keep its internal energy or to keep it temperature constant. The system must get some amount of energy in terms of heat. Okay, so that means when system actually works on the surroundings, system have to get some amount of heat to keep its temperature constant. And that means you have to give the system a sufficient time so that system can remain it can remain at a constant internal energy state. That means it must the system must fixed its internal energy. So that means you have to give the system proper time so that it can get the proper amount of energy from the surroundings, or it can release proper amount of energy to the surroundings, so that its internal energy doesn't change. So that means this process is a slow process, and the equation of state, that means the relation between pressure, volume and temperature, that we use is PV equals to constant. As our temperature is constant, that means Boyle's law holds good here, so PV is a constant for us for this kind of process. Now I have shown here an isothermal process. That process starts from A, that is P1 V1 T1, and it ends at the state P2 V2 and temperature T1, and there is an intermediate state called PV and T1. So we know the work done, that is W equals to integration of PdV. As we know, dW is PdV, pressure times change in volume. So to get the work done, we have to integrate this, and at A, the equation we can write is P1 V1 equals to nR T1, that is ideal gas equation. At B, it will be P2 V2 equals to nR into T1, and at in between state, that is PV equals to nR T1. Okay, now for work done, W equals to our integration V1 to V2, because we are starting from volume V1 and we are finally going to reach to the volume V2. So integration will be performed over the volume, that is from V1 to V2 PdV. Now find the value of P from this equation. P is your nR T1 by V. Just put it here. Okay, so nR and T1, this three term is constant for us, so just keep these things out of the equation. That will be your V1 to V2 integration dV by V. Okay, as you know, this integration of 1 by x dx is your ln x. Ln means that is log to the base e, so it is 1 by V dV, that means that will be your ln V. Integration will start from V1 to V2. Okay, so that is your initial volume to final volume. Now how to use this limit to the equation? You have to put the upper limit first, that means you will get ln V2, then put a negative sign between minus, put the lower limit, that means ln V1. So that's how we use the limit. So nR T1 ln V2 by minus V1, ln V2 minus V1 is your ln V2 by V1. So final value of the work done is W equals to nR T1 ln, again P1 V1 equals to P2 V2, since Boyle's law holds good here. So that means V2 by V1 is your P1 by P2. Just put this here, you will get nR T1 ln P1 by P2. Okay, so this is all about the isothermal process, and next process that we will going to discuss is our adiabatic process. Okay, so adiabatic process, as I already mentioned, there is no heat exchange is allowed for this type of process. That means you don't you just don't allow the system to take or to release some amount of heat from the surroundings or to the surroundings. So that means this process is really fast, because if you allow some time, the system will going to leave or going to get some amount of heat from the surrounding. So you don't need to give the system so much time that it can exchange the heat with the surroundings. Okay, so that means this is a faster process, and the constraint of this process is Q equals to 0, and from the first law it is clear that dW is minus du. That means work is done in expense of internal energy. That means system does the work, and it does it in expense of its internal energy. Okay, so that is the adiabatic process. So since work is done in expense of internal energy, that means the internal energy can get reduced or it can be increased depending upon the amount of work is done on the system or amount of work done by the system. Okay, so that means if internal energy changes, that means temperature of the system will change. Okay, so now we have to find the equation of state for this type of process. As we know, this PV equals to constant will not hold good for this time because temperature is not constant. So now we will start to find the equation of state for this type of process. Okay, So now dq equals to 0. So we just have the first law of thermodynamics, that is dq equals to du plus dw. We just put it here. So du plus dw is 0, however. Du is again CVDT for 1 mole of gas, and dw is PdV. So that means CVDT plus PdV equals to 0. Just write down, just take it as equation number 1. Now for 1 mole ideal gas, PV equals to RT, and as we can understand, the pressure volume both can be both can change in this process. So if you differentiate the equation, you will have to differentiate these two things. First one, just take the p constant and differentiate, you will get pdv. Next, take the v constant and differentiate, you will get vdp. So as a whole, differentiating pv will give you pdv plus vdp equals to r is your cp minus cv, already just who derived, and differentiating t will get dt. Okay, now just rearrange this term, pdv plus vdt cp dt minus cv dt, just rearrange this term. Okay, so you will get, just took this equation term to left and took this term to the right, you will get pdv plus equals to c plus cvdt equals to cpdt minus vdp. And as you know, pdv plus cvdt is your 0, then when this term is 0 and this term is equal to this term, and that means this term will also equal to 0. So now we have two equation, pdv plus cvdt equals to 0 and cpdt minus vdp equals to 0. So from the first equation we will get pdv equals to minus cvdt, and second equation we will get vdp equals to cpdt. Now just divide these two equation, you will get, just divide this equation with that one, you will, sorry, that equation with this one. So you will get v by p and dp by dv equals to minus cp by cv, and cp by cv is our gamma, that is the ratio of two specific heat capacity, molar specific heat capacity. So just again rearrange this term, take dp by p here and just take dv, v by dv to the left, to the right, you will get minus gamma, that is cp by cv your minus gamma, and it will be your dv by v. Okay, just integrate both the side of the equation. 1 by x dx was your ln x, so 1 by p dp will be your ln p, minus of gamma, that one is constant, dv by v will give you ln v, and there will be a integrating constant c. Okay, now just take this equation to the left, you will get ln p plus gamma ln v, and gamma is just inserted into the log, that means it will be converted to the power. So ln p plus ln v to the power gamma equals to constant. Okay, so here I have just shown another, just make a step jump, that is your, that will be your ln p plus gamma ln v equals to c, and next it will be ln p plus ln v to the power gamma equals to c. This gamma will be inserted inside the log and it will become the power. Okay, so that means this is log a plus log b, that will be your log a into b, pv to the power gamma equals to c, that is your constant. Ln pv to the power gamma equals to constant, that means this pv to the power gamma will be constant again. Now just you have the equation for ideal gas, pv equals to nRT, just put this value here, you will get a relation for temperature and volume. And again, by getting this type of relation from the ideal gas equation, we will reach to the variation with pressure and with temperature, that means p, and relation between p and t will be achieved by using this. Now we already have the relation, that means equation of state. Now it is time to find the work done during the process. The work done is very simple, that is integration of pdv. Now this is the adiabatic process starting from p1 v1 t1 and it ends at p2 v2 and t2. Then pressure, volume, temperature all has changed. Now equation of state at A, that will be P1 V1 to the power gamma equals to constant, that is K. At B, that is P2 V2 to the power gamma equals to constant. At any point in between, that will be P, V and T, and it will be PV to the power gamma equals to K. And by using ideal gas equation at A, we will get P1 V1 equals to nR T1, and at B we will get P2 V2 equals to nR T2. Okay, this all set of equation that we already have. Now work done W equals to integration V1 to V2 PdV. Now here also we have started from the volume V1 and we will end at the volume at V2. Okay, so just change the P from this equation. P equals to your K by V to the power gamma. Just put it here, and as we know, the integration of x to the power n dx. So just take the K out of the integration. That will be your integration of V1 to V2 V to the power minus gamma. Okay, we have V at the denominator, so that means it will be V to the power minus gamma dV, and by integrating that we will get K V to the power minus gamma plus 1 by minus gamma plus 1. Since the integration of x to the power n dx equals to your x to the power n plus 1 by n plus 1, just comparing with the equation, it is your v to the power minus gamma, here it is x to the power n, so x to the power n plus 1 by n plus 1, so you will get v to the power minus gamma plus 1 by minus gamma plus 1. Okay, so again the starting from v1 to v2, just put upper limit here. Okay, this is again a constant term, just take it out. So k by 1 minus gamma, just put upper limit v2 to the power 1 minus gamma, put a minus sign between them, and put the lower limit again, v1 to the power 1 minus gamma. Okay, now v2 to the power 1 minus gamma is your v2 by v2 to the power gamma, and v1 to the power 1 minus gamma is your v1 by v1 to the power gamma. Okay, so just again multiply the k inside, so you will get v2 into, you will have the k here, then that means k by v2 to the power gamma minus v1 into k by v1 to the power gamma, and k by v2 to the power gamma is your p2, k by v2 to the power gamma is your p2, and k by v1 to the power gamma is p1. So you will get p2 here and p1 here, p2 v2 minus p1 v1, and p2 v2 equals to nr t2, and p1 v1 is nr t1. So that means nr t2. Okay, we just missed a value n here, that is n nr t2 minus nr t1. Just take the nr common, so nr by 1 minus gamma will be ct in multiplied by t2 minus t1. That will be the total work done in the adiabatic process. Okay, so that was all about the adiabatic process. That means okay, one thing just I forgot to mention, that as you just see this, during the adiabatic process work is done, and work is done in expense of internal energy. That means internal energy must be changed of the system. So that means the and always also you know about the internal energy is directly related with the temperature of the system. That means if the some amount of work is done on the system, that means internal energy of the system will be increased, and that will actually increase the temperature of the system. So a system will get hotter if some amount of work is done on the system in adiabatic process, and if system did do some amount of work on the surroundings, that means system will lose some amount of internal energy and it will get cooler. Okay, so this actually change in temperature of the system happens during the work done in the adiabatic process. Okay, I think it's all clear, all thing is covered about the adiabatic process and isothermal process. So rest of the two processes are isochoric process, that is where volume is constant, that means the change in volume dv is 0, that means dw is p times dv is 0, that means volume doesn't change, that means work is not done during the isochoric process. Okay, and isochoric process is shown like a by a vertical line in a PV diagram. Okay, since volume remains constant but system changes its pressure, so that is your P1V and it is P2V. The also temperature can change, that is T1 and it can be T2. Okay, now next one is isobaric process where pressure is constant, so work done is dw equals to pdv, so w equals to integration of v1 to v2 pdv. Now p is constant, just take it out of the integration, p integration v1 to v2 dv. As we know, integration of dv is v, so v starting from v1 to v2, just you will get p of v2 minus v1. Just put upper limit, then minus, and then put the lower limit, you will get v2 minus v1. So this is quite simple for isobaric process to find out the work done. Now in PV diagram, that is a parallel line with the volume axis. Okay, since pressure is constant, so this is starting from PV1, it will end at PV2, again it is T1, and again temperature is T2 here. So this is a isobaric process. Okay, so last thing that we will discuss in our today's discussion, and then we will just finish it off. So that is the adiabats. Adiabats means this curve in the PV diagram, that is called adiabats, and the process shown in the PV diagram, isothermal process shown in the PV diagram, is called isotherm. So which one is more steeper? That means in which process pressure and volume changes faster compared to the other, that we will look here. For the isothermal process, the equation of state is PV equals to constant. Just differentiate that, you will get PdV plus VdP equals to 0. So just find the dP by dV. Since for the PV diagram, dP by dV is your slope of the curve. Okay, as we know, slope is your height by base. Height is your P, and V is your base of any triangle. If you draw a triangle in PV diagram, you will get the height in the P axis, and you will get the volume as a base. Okay, so then dP by dV is your work slope of the curve. That means you will get from here dP by dV is your minus P by V. So the slope of the isotherm is simply minus P by V. Now for adiabatic process, your equation of state is PV to the power gamma equals to constant. Now this two term, first we will keep this v to the power gamma constant and differentiate dp p, so we will get dp p to the power gamma, and then we will take this p constant and we will differentiate v to the power gamma. We will get gamma v to the power gamma minus 1, because as we know dd x of x to the power n gives some kind of this value, n x to the power n minus 1. So just keep it in mind, this gamma power will come out and power will reduced by 1, v to the power gamma minus 1 dv equals to 0. Now you just take v to the power gamma minus 1 common from this two equation. From this two term you will get vdp from the first one, because v to the power gamma minus 1 is taken out from this v to the power gamma, so v will remain there, and from the second term it will be gamma p dv. Okay, so if you take this term to 0, so you will get dP by dV is minus gamma P by V, and so that means this one is slope of the adiabat. Slope of the adiabat is gamma times, that will be gamma times minus P by V, and as you can see there is minus P by V is slope of the isotherm, so that will be gamma multiplied by the slope of the isotherm. So that means, so adiabats are more steeper than any isotherm. Okay, so this is all about the thermodynamics, and this is the end of the first law of thermodynamics. In our next lecture we will actually learn about the second law of thermodynamics. Okay, so if you like this video, please press the like button and subscribe my channel. Thank you.